Solutions and colligative properties. So before we get too into this, I want to make sure you understand the solution vocabulary. First off, a solution is two or more substances in a homogeneous mixture that will not separate. It's made up of both a solute and a solvent. A solvent is the thing that is more, it is your dissolving medium, and actually water is considered the universal solvent. The solute is the material being dissolved, and so that's usually the thing that's less. So if we're making a Kool-Aid water mixture, for example, Kool-Aid would be your solute and water would be your solvent. Now, electrolytes is an ionic substance that can conduct electricity when dissolved because they dissociate into ions. While ionic, just to recall from first semester, is a metal bonded to a nonmetal, or metal bonded to a polyatomic ion. So if your compound starts with a metal, it is probably ionic. Non-electrolytes are covalent substances that don't conduct electricity. So covalent is going to be non-metals only. Okay, so we have these two pictures. And you can see you have a solid plus a liquid making a solution. And so I want you to be familiar how the solid basically splits up. So we have it in solid form, but it splits up within the solution. Okay, and so a solution like this one would conduct electricity. So over on this picture, we can see three different light bulbs. We see this one that is off, this one that is on, and this one that's in between. So ethanol is C2H5OH. So it is considered an alcohol. It starts with a non-metal. And so you can see that the light bulb does not go on. It's non-electrolyte. And you can see that these compounds stay together. Now KCl starts with a metal. It is ionic. And so you could see the pluses would be your Ks and the negatives could be your chlorines. So this one will conduct electricity and is considered electrolytic. Then on the far right here, we have the acetic acid solution. So acids are going to conduct electricity. Strong acids will conduct strongly and weak acids will conduct weakly. And we'll get into that in a whole separate unit. So if we look at what we've done, we've talked about states of matter. And there are three main states of matter. These are all the different combinations we could come up with for different types of solutions. So a mixture of gas could be air. A gas bubbled into a liquid could be like an aquarium, or chlorine is bubbled into water at a water treatment plant. Gas in a solid could be like nitrogen in a Twinkie. It makes it kind of spongy. Or think about the jet puffed marshmallows. Liquid in a gas is like a water vapor or a cloud. Liquid in liquid is ethanol and water, like an alcoholic beverage, or antifreeze in water, which is in your car. A liquid and solid is like the old days. We used to put actually mercury and silver in our fillings. Now we pretty much use composites. A solid and a gas is something like diesel fumes. And so as you can see that particulate in the back of a vehicle. Solid and a liquid that's one way we can make an acid. I have the example here of citric acid. And a solid is like an alloy. Mostly what we're going to deal with on this current part of the unit is solids in a liquid. So I do want you to be able to solve solution calculations. You'll notice we're reviewing molarity. Notice molarity has a large M, and it is the moles of solute per volume of solution. Now what's new is molality, difference of one letter. It's a small letter M, is the moles of solute per kilograms of solvent. So because we're going to deal with kilograms, it does help to know the density of water is 1 gram per milliliter or 1 kilogram per liter. We also know that there are 1,000 grams in a kilogram, and that can help us with figuring out that bottom part. So I have one molarity review question. So what is the molarity of 1 liter of water that has 117 grams of NaCl added to it? So we take 117 grams of NaCl. 1 mole NaCl is equal to 58.5 grams. And we find that to be 2 moles. So the molarity is equal to 2 moles over 1 liter. So it is a 2m, large M, or a 2 molar solution. Okay, the next one, how many grams of NaCl are needed to make a 250 milliliter 0.5 molar solution? So we can start with our equation. So I do know that the M is 0.5, and I need to make that 250 mils into kilograms. Okay, so if I take 250 mils of water, I can multiply by the density. So this is the density, and then 1,000 grams in a kilogram. So if I solve that out, then I could find that it is 0.25 kilograms. So 0.25 would go on the bottom. So we're going to cross multiply, and we find it's 0.125 moles. And then we're going to go ahead and convert that back to NaCl using our molar mass. So I found it to be 7.31 grams of NaCl. So solution concentrations, we also need to know something called a mole fraction. It's represented by the letter X. So if I have only two components, it'd be a solute and a solvent. This mole fraction should add up to 1. It's kind of like the percent composition where you just take the part over the whole. And so if I look at this example, what is the mole fraction for each substance if you have 2 moles of NaCl and 3 moles of water? So NaCl is my solute and water is my solvent. My solute is 2 moles of NaCl, and it's 2 plus 3 on the bottom, so it ends up being 0.4. And then my water is 3 moles on top, 2 plus 3 on the bottom, 0.6, and that adds up to 1. A lot of times you'll see something written as percent by mass or percent by volume. I've seen this a lot in the bio world. And again, it's kind of like the percent composition idea. You take your mass of solute divided by the mass of solution, or the volume of solute over the volume of solution. So for example, vinegar is 5% acetic acid. So what we're saying is you have 5 grams of acetic acid per 100 grams of solution. So I have an example problem. 300 grams of NaCl, 400 grams of solution. What is the mass percent? So you take 300 divided by 400 times 100, and you find it to be 75%. Okay, so this next part is a little deceiving. It's a little bit trickier than you may think. So for colligative properties, which is a fancy way of saying when we add a compound like a salt to a solution that we change its properties. And ultimately we can change its freezing point or its boiling point. So I is known as the Van 't Hoff factor. And what we're going to do is figure out how to determine how many ions something has. Now, if it is covalently bonded, I is going to be 1. So the way I like to do these is I look at my compound and I first go, does it start with a metal or a non-metal? If it starts with a metal, then I'm going to have to figure out how many of each ion we have. So I have 1 sodium and 1 chlorine. 1 plus 1 is 2. Okay, so let's say I look at the next one. Calcium, that is a metal. Okay, so I have 3 calcium ions and I have 2 phosphates. So 2 plus 3 is 5. So be careful with polyions. If you have more than 2 elements, you probably have a polyion. You're going to ignore that superscript or that subscript for the PO4. We're just looking at how many of those PO4 groups. And actually having an I of 5 is pretty high for these. So if we look at the next one, we have K2CO3. So we have 1 potassium, and we only have 1 carbonate. So 2 plus 1 is 3. Okay, and we look at the next one. It starts with a non-metal, so I is 1. Okay, so often I like to add a little extra practice. So you can go ahead and write these down. I think it helps to add those. And so see if you can figure out I for each of these, and then I'll write down the answer. Okay, so for the first one, we have K3P. So we have 3 Ks and 1 P. So 3 plus 1 is 4. Next one starts with carbon. So I is 1. Next one, we have 1 magnesium, 2 cyanide ions. 1 plus 2 is 3. Next one, we have 1 sodium and 1 acetate ion. It looks kind of scary. So it's 2. That starts with a nonmetal. I is 1. So we're going to use that information to find our freezing point depression or boiling point elevation. So you find that solutes lower the freezing point of solution. So if we look at Fp nu is equal to 0 minus mkFpi. Now if we're doing a lab, you would actually need to know what is the true freezing point. Okay, so this is the actual freezing point without anything in your solution. So if we're doing something other than water, it would be different than 0. M is molality. KFP is this constant, which it is for water is 1.86. And then I is finding the number of ions. So here's a typical problem. Determine the freezing point of a solution of 60 grams of glucose dissolved in 80 grams of water. So this one, we're going to ultimately use this equation. Now we do have to find our molality. So 60 grams C6H12O6. So 1 mole over 180 grams. I found it to be 0.33 moles. And then 80 grams of water. Now we're going to go ahead and convert that to kilograms. So that's 0.08 kg. So molality is going to be dividing those two. That's 4.13 m. So now we have 0 minus 4.13. KFP is a constant, just like the gas law constant. So 1.86. And then I, for this one, because it starts with C, it's a nonmetal, I is 1. So our new freezing point is going to be a negative 6.68 degrees C. Okay, so that is how de-icer works. So it actually lowers the freezing point on the roads. Now we can do something similar with boiling point. So the boiling point is actually raised if we add a salt. So here we have our new boiling point is equal to 100 plus mkBpi. So again, 100 is the pure substance boiling point, so that would be true for water. M is molality, KBP is its own constant, and I is the number of ions. I've also seen the KBP written as 0.52, and I've written as 0.512 as well. Usually I'll use it as 0.51, but I just want you to have the heads up. Sometimes you see it in a different way. So what is expected boiling point of a brine solution containing 30 grams of KBr dissolved in 100 grams of water? So again, we're going to have to convert our mole KBr to grams to moles. So it's 0.252 moles. And we have 100 grams of water. So 1,000 grams in a kilogram. That's 0.1. So the molality is 0.252 over 0.1. Okay, so that's part of it. So now we're going to find our new boiling point, which is 100 plus the molality times my constant times I, which would be 2, 1K and 1 BR. And we find it to be 102.6 degrees C. So it does raise your boiling point, but it's not going to raise it a ginormous amount. So if you have a crazy high number, you've probably messed up. So that's just something to keep in mind. You might have heard that adding salt to a boiling pot of water raises your boiling point. And, theoretically that could, but I want you to think about the amount of salt you add. You probably just add a sprinkle. It's probably not going to make a huge difference in that pot. However, in professional restaurants, they had a lot more salt than a home cook. Possibly it does increase that boiling point. So you might see if just calculating the molality of a solution from a temperature change. There's also sometimes a web design question where it just wants to know by how much did it change. So you can find that delta T is equal to your molality times that constant, either freezing point or boiling point, times I. And I know the freezing point depression lab also uses this equation. And one last thing, we can find the molar mass directly by taking the boiling point or freezing point constant times the grams of solute divided by delta T times the kilograms of solvent. You could also use the full equation like I showed you. So it's kind of up to you on how you want to handle it. So let's say you want to check to see if a new sports drink really has glucose in it instead of sucrose. You boil it, and it boils at 100.16 degrees C, and you read the label and find there are 50 grams per liter. So molar mass, and so we boiled it, so I'm going to use the boiling point constant. Grams of solute is 50. My delta T is going to be 100.16 minus 100. So it's going to be 0.16. And then liter, 1 liter, if I multiply by density, it's 1 kilogram. So if I solve that out, I find it to be 159.4. By the way, the units of molar mass are grams per mole. And you find that that's closer to the glucose molar mass than sucrose. Okay, so I do have some practice problems posted on CK12. This worksheet has more like your molality kind of practice, and there is a key. And then this is like freezing point, boiling point practice with a key. I also have posted some videos that can help you. And if you ever have any questions, please feel free and reach out.